Have you ever heard the word tensor thrown around, in conversations about AI or physics, and you just kind of nod along? Well, today we're going to pull back the curtain on this thing, and I promise it's way less intimidating than it sounds.
So what exactly is a tensor? Is it some ridiculously complex, high-level math that only a handful of geniuses on the planet really get? Nah, not at all. It's actually a surprisingly elegant and simple idea, and by the time we're done here, you're going to see it too.
And look, we're not going to just throw you into the deep end here. The secret to really getting a handle on tensors is to start with something way more familiar, something you've definitely seen before.
Okay, so what's a tensor anyway? Well, to get there, let's kick things off with a familiar building block, the vector. So, a vector. Most of us, right, we learned that a vector is basically an arrow. It's got a length, which tells you its magnitude, how strong or how fast something is, and it has a direction, which tells you, well, which way it's going. Think about velocity or a force. Yeah, it's that arrow. Pretty straightforward. But, and this is a big but, if we're going to climb the ladder all the way up to tensors, that simple arrow idea isn't quite enough. It's a great starting point for sure, but we need to look at it from a slightly different angle.
So let's move beyond the arrow. It's time to introduce a couple of new ideas: components and basis vectors.
To talk about a vector with any real precision, we need a map, a frame of reference. That's our coordinate system, your good old x, y, and z axes. And this map comes with its own special rulers, these little things called basis vectors. Just think of them as one perfect step in the x direction, one perfect step in the y direction, and so on. They're like the fundamental Lego bricks for building any vector you can imagine. Right, so we've got our grid and we've got our standard steps. Now what? How do we use this whole setup to describe our original vector? How do we figure out its parts, or what we call its components?
One really cool way to visualize this is the shadow analogy. Imagine you've got your vector, and you shine a flashlight straight down from the ceiling. The shadow that vector casts on the floor, the x-axis, well, that's your x component. Then do it again, but shine a light from the side wall. The shadow it makes on the other wall, the y-axis, that's the y component. It's literally how much of the vector is pointing in each direction.
All right, let's talk more about components and basis vectors. The shadow thing is pretty cool, but honestly, there's an even more intuitive way to think about this that I think makes it all just click. Okay, picture this. You are standing at the very beginning of the vector, at its tail. Your mission is to walk to the tip, but there's a catch. You can only walk along the grid lines. So first, how many of those standard x direction steps do you have to take? Let's say 4 steps east. Okay, you're there. Now, from that point, how many y direction steps north do you need to take to finally land on the tip? Maybe it's 3. And that's it. That's the whole game. Those numbers, 4 and 3, those are the vector's components. You can think of them as a recipe, a set of instructions. Go 4 steps in the x direction, then 3 steps in the y direction, and you've perfectly recreated the vector. So what this really means, and this is the big takeaway here, is that this arrow is the exact same thing as this simple list of numbers, 4, 3, and 0. They're not just related, they are 2 different ways of saying the exact same thing, an arrow or a list of numbers. Same object. All right, now we can introduce the tensor family. You're about to see the pattern that connects everything. Now that we've reframed a vector as just a list of numbers, a set of instructions, well, that's the key that unlocks the entire idea of a tensor. So let's build this up. Think about a simple number, like the temperature in your room. It's just a number. It has no direction. We call this a scalar, but in our new language, it's a tensor of rank 0. 0 directions, 0 indices. Now, what about our vector? It's a list of numbers, right? It has 1 index for each number, the x component, the y component, and so on. So a vector is a tensor of rank 1. See the pattern? The rank is just counting how many directions or indices you need to pick out a single number in the object. And once you see that pattern, the whole mystery of the tensor just evaporates. It's just the next step. A rank 0 tensor, a scalar, is 1 number. A rank 1 tensor, a vector, is a list of 3 numbers in 3D space. So what's a rank 2 tensor? Well, it's a grid of 3 by 3 numbers, 9 components in total. Each component now needs 2 indices to specify it, kind of like a location in a spreadsheet. Why would you need that? Well, think about describing the stress in a material. You need to know the direction of the force, sure, but you also need to know the direction of the surface it's pushing on.
That's 2 directions, 2 indices. That's a rank 2 tensor. And yeah, you can have rank 3, rank 4. It's all the same idea, just with more indices.
Okay, so now we're getting to the big stuff. The facts of the universe. Why does any of this matter? This whole pattern thing is neat, but so what? Why is this such a big deal?
I mean, seriously, why is this structure so important? Why did we go to all the trouble of breaking down a simple arrow into this whole system of components and coordinate grids?
Because here's the beautiful part. Let's say you and I are both looking at the same exact physical thing, that arrow. But maybe my head is tilted, so my personal grid, my coordinate system, is rotated compared to yours. The components I measure, my walking instructions, are going to be different from the ones you measure.
And this is everything. Even though our components, our lists of numbers, can change, the underlying tensor, the physical reality of that arrow, does not. It stays the same. The arrow itself doesn't care how we're looking at it. That thing, the thing that doesn't change, that is the tensor.
Our lists of numbers might look different, sure, but they transform in a perfectly predictable mathematical way so that the underlying truth remains constant for everyone, no matter their perspective. It was this powerful characteristic that caused the physicists Lillian Lieber to call tensors the facts of the universe. They describe something real and objective, independent of the observer.
So, you see, a tensor is so much more than just a grid of numbers. It's a language for describing the fundamental truths of our world, truths that don't change no matter how you look at them. And that kind of makes you wonder, right? What other facts of the universe are out there, just waiting for us to find the right language to describe them?